Hi ET370. I wanted to give a short little intro to aliasing and then do the homework problem 9.25 for you guys. I felt it was a little rushed in class, so let's look at what aliasing is. So aliasing is basically a problem when what you think is not what reality is. And so let's say you're sampling a signal using your microcontroller. If you're not sampling fast enough, you're going to think the signal is some frequency, not what reality is. And so the little more formal statement, aliasing is a problem when the apparent frequency, or what you think, differs from the actual frequency f of a signal. Okay? And like I said, this is a problem when your sampling rate, or fs, is too small. So aliasing depends on the sampling rate of the microcontroller. In this case, it's our Arduino. The other thing that we have to be concerned with is the relative value. And so you can be safe if your sampling rate is greater than 2 times the frequency, but aliasing will occur if it's less than or equal to 2f. And this 2f actually has a special name. It's called the Nyquist Frequency. So you want to sample greater than 2f. In fact, you actually want to sample between 5 to 20 times f if you really want to make sure that no aliasing occurs. And so let's look at an example of some plots that I made using MATLAB to see what I'm talking about. Remember, there's 3 frequencies going on. There's f, there's the real signal, this is what you really want to see. There's fa, which is what you think you're seeing, and then there's fs, which is the sampling rate of your microcontroller. Okay, so 3 different frequencies we're talking about. Okay, let's look at an example plot. So let's look at this first plot and see what's going on. So if I look over here, I see there's f, or this signal with a frequency f, and this is our actual signal coming in. Imagine it's maybe a linear transducer that's vibrating, and we want to see that linear transducer movement, and so we sample it at some frequency. In this case, it's 20 times f, which is much greater than 2f, so there shouldn't be any problem. And you can see there's 20 little bubbles per 1 period, okay, if we were to count. So what does that mean? That means what you think is what you get. Fa equals f. Alright, what you think is what you get because our sampling rate is much, much greater than 2f. Okay, let's slow the sampling rate down. We'll keep f the same, but now we'll sample at 5 times f, and you can see there's dots here that are connecting, and if I connect the dots, yeah, I can still make out the signal. I can still tell that f is what it is, right? So what I think is still what I get, and it's fs, the sampling, is still greater than 2 times the actual frequency. All right. Now let's say I were to decrease the sampling rate even more. What would happen? In this case, this is bad, right? Here, fa is not a reality. Reality is this signal here, and fa, well, it just thinks it's all 0. So definitely we have an aliasing problem, and this occurs when the sampling rate is 2 times the frequency. Right? We don't even know what fa is in this case. Now let's go a little bit further. Let's decrease it even more. So now we go to 1.2f. Definitely, again, aliasing occurs because we're less than the Nyquist frequency. And in this case, fa is going to be less than f, and let's see what we get. We see this. And so that means that there's 1.2 samples for every period here, okay, or the inverse of that. And you actually, if you were to connect the dots, you would see that the frequency that you think is occurring is actually slower than f, right? If you look at these connected blue dots here, it's a slower frequency than f. So fa is not f, it's actually less than f. Again, 3 frequencies: reality, what you think, and the sampling rate. Okay. So you can definitely see here in these 4 plots that there's a problem if you sample too slow. So how would we look at that on a plot of fa versus f? And so let's draw it here. So if I were to draw on the y-axis fa and on the x-axis f, what I would see is something that looks like this. And I got to put my units. If I'm low, if I have low frequency here, the actual frequency is kind of very slow, I would see a 1-to-1 relationship between fa and fs. Okay? And so again, fa is what I think, and f is what really is happening. And if it's 1-to-1, that means they're equal, right? fa equals f, right here, no problem. Now let's say we get to the point where we hit that Nyquist value where Fs is equal to 2f, or I should say f is equal to 1/2 Fs is the same thing. We get to a point where, aliasing occurs, and instead of continuing on this good line, we actually start decreasing, right? And we saw that in that fourth example. As we get lower and lower and lower, we hit a point, and actually it starts increasing again, decreasing, and increasing again, so on and so forth. So this had a 1-to-1 slope, this has a minus 1-to-1, this has a 1-to-1, minus 1-to-1, and so on and so forth. So this is actually the plot of how what you think and what reality is differs after this value. And here this is when f equals fs, and then 1.5, and so on and so forth. So really, after this point here, this is all bad because aliasing occurs. And this part here is good because fa equals f, what you think is reality. Okay? Let's do an example to kind of put some numbers on it, or hopefully get a little bit more intuition. So the example 9.25, and this is in your homework, reads 9.25. Let's say you have a 10 kilohertz signal or sine wave, and it is sampled. Okay, and what we want to know is, well, what do we think it is? So what is FA? And we want to determine it for three cases. FA if Fs is equal to 11 kilohertz. So that's A. If our sampling rate is 8 kilohertz. And C, Fs is equal to 40 kilohertz. Okay. We also want to know, does aliasing occur for all three cases? All right. So if we look at these numbers, we see a larger number, a smaller number, and then a very large number. So my guess is that maybe aliasing occurs for the first one, or maybe the second one for sure. The middle one, of the A, I'm not sure. We'll have to check. But this one, maybe not, because the sampling rate is high enough. All right. So let's look at A first. And so what's our condition? Aliasing occurs if Fs is less than 2f. If that's true, then we're going to have a problem. All right, so what are we given? We're given that f is 10 kilohertz. That's just constant for all three cases. F is 10 kilohertz. That's the actual signal, actual sine wave coming in. All right, and in part A, Fs, the sampling rate is 11 kilohertz. All right. So let's calculate 2f. We want to calculate the right side of this equation. 2f, that's pretty easy. That's just 20 kilohertz. And we see that 11 is less than 20, which means that Fs is less than 2f. That means, bing, 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 yes, aliasing occurs. So we're going to have a problem. We're going to know that Fa and F, the actual, is not going to be the same. So let's get a number on what FA would be. What do we think it's going to be, even though we know it's not correct? All right, so we're going to rotate the paper sideways here, and we're going to plot, let's just replot F versus FA, and we'll draw our relationship between FA and F, okay? And so what's going on here is that our F, this is the point where F equals Fs, which equals to 11 kilohertz. Okay, that's at this point here. All right. Now, what about at this point? This is half of this. Okay, this is where F equals 1/2 Fs. Okay. All right. And then what are we looking at? We're looking at when F is 10 kilohertz. So we're around it. This is 11. This is what, 5.5. 10 is about here. So we want to know, what is this value of Fa when F equals 10 kilohertz? And you can see it's definitely not 10, right? If we were here, then it would be 10. We'd be happy because F equals Fa, but in this case it's not. All right. So how do we figure this out? It's not too bad. This is a slope of -1 to 1. And this here, because it's that same slope, this should also be 11 kilohertz. Okay, so if I use our little linear y equals mx plus b, not too bad here. Y is going to be FA. The slope is a -1 slope. The x-axis is f plus b, which is now 11 kilohertz. And I'll just plug in my point, 10. So FA equals -1 times 10 kilohertz plus 11 kilohertz. So FA equals -10 plus 1, that's that's 1 kilohertz. Okay, so what is that saying? It's saying because the sampling rate is not fast enough, FA does not equal F. In fact, FA is less than half. Because the sampling is not fast enough, then FA is not equal F, and in this case, FA is actually less than F, right? Because 1 is less than 11. Okay, so that's part A. Let's do part B here, and so we look at part B asks for 8. Well, definitely if 11 wasn't fast enough, 8's not going to be fast enough. We're probably over here. Okay, are we going to get aliasing? For sure, I'm pretty sure. So let's go back to here. So part B, FS is what? FS is equal to 8 kilohertz now. Okay, and so we look at 8, and that's less than 20. So yes, FS is less than 2F, and so we got aliasing. Check. Okay, let's look again at our F versus FA, 1-to-1 relationship here. This is still 11, this is not 11 kilohertz. This is now 8 kilohertz. This is when F equals to Fs. So this point is now at 8 kilohertz. Okay, and our point of interest is still 10 kilohertz. Okay, so our point of interest is now 10 kilohertz. Okay, and so this is the point, FA, that we are interested in. Notice we're on a different line here, but because this is still a 1-to-1 scale, this point is now, instead of positive 11 like this point was, it's now negative 8 kilohertz. Okay, whatever this point is over here, because it's a 1-to-1 relationship. Okay, so we have y equals mx plus b, which is FA equals positive 1, this is a positive 1 slope now, times F plus negative 8 kilohertz. And so now we can plug in our value in here. FA equals positive 1 times 10 minus 8, so FA is equal to 2 kilohertz. Again, it's not the same as F, right? Had it been the same as F, we would see just 10 kilohertz, right? Okay, good. Let's do the last one, part C. So if we look at part C, now we're looking at when Fs is 40 kilohertz. Okay, so part C, Fs equals 40 kilohertz. Okay, now let's look at 40 compared to 20. 40 is now greater than 20, so that means Fs is greater than 2F, and we go, no, aliasing does not occur. Not occur. Well, if aliasing doesn't occur, we don't even have to use this plot anymore. We're in this region over here, and so we already know that FA equals F is equal to the 10 kilohertz. Okay, so what do you think is reality? Good. All right, guys, I hope this helped, and see you in class.